Hello? AJ, can you hear me?
Yes, I can.
Awesome, thanks. I think I have to use this weird microphone that I had to bring because one of the other teachers told me the mic was off in this room. So I'll probably have to stand near the podium, which is a little weird.
Nobody showed up.
Yeah, we'll see. We got AJ and Aiden online, and you so far.
Man. I know people that live in the same apartment building as me and they're not here. All you have to do is walk. They're not
Yeah.
right?
Well, that's the thing about the recording, right?
Yeah.
I was wondering if I was going to teach to a recording,
Right.
basically.
I don't know how to do that. I just like
Well, so another faculty told me that the classroom's recording wasn't working, or the audio, so I brought this.
Okay.
So I'm going to have to stand here. So no writing on the board, unfortunately.
Are most classes not happening today?
I don't know what everybody's doing. I taught another class before this. It's a computer lab class, and if they didn't come, then they weren't going to make any progress. So I wasn't going to move that class online, so I was going to be here anyway. So figure treat it like normal. But the weird thing was the university yesterday told faculty, it's like, okay, yeah, the weather's bad. Just communicate with your students what you're going to do. But then this morning, and so that's why I said, oh yeah, it'll just be normal and recorded otherwise.
Yeah.
But then I saw it was quite bad this morning, and then they canceled before 10. And I was like, okay, I better say it's optional so you can join live stream. But
Yeah, well, I was walking.
but then I thought, what does that mean? Nobody's going to be here. But yeah.
It's kind of a nice surprise storm, you know. So like, you know,
Yeah, not for me.
yeah, not for you.
Getting a little feedback. I wonder why that is. Okay, I muted everybody but me. I see that we have now looks like seven or so of us online, so that's pretty good. So here it is, 4 o'clock. So thanks for joining. I'm gonna present here to Garrett and to you all that are here. It'll also be recorded, hopefully with audio, but if not, I'm recording it on Teams, so if need to after the fact, I can upload this Teams video to Canvas for those that weren't here. So we're going to talk about sedimentary rocks today, and I'm going to be stuck here at the podium because I have to use this weird microphone that you guys can probably see me on. So it's going to be hard for me to write on the board. If I need to, I could get over there and do it, but I'll try to avoid that. I guess otherwise, I sort of have chat open. So if you need to ask me a question, you can do that, or you can unmute yourself and ask the question as well. Feel free to pipe in. There's not that many of us. Just after you're done, try to mute yourself again. A few reminders as we move forward. So I did check through quiz 2, which will be coming up pretty soon. It seems to be on track to be open up next week. It goes through sedimentary rocks, so what we're talking about now. We will also be having an activity on sedimentary rocks next Monday, so I would advise not taking the quiz until after Monday's class. And the stuff we're going through here today is going to help us with doing that sedimentary rocks and environments of deposition activity. And so as we move through this stuff, we're going to be talking about what type of rock is the sedimentary rock, and what does that tell us about the environment where that sediment was formed or deposited, mostly deposited, but sometimes formed. What does that tell you about the environment of formation, and how do we know this? So those are the 3 overarching things to take away from today. And so most depositional environments are in low relief places. So if we look around the world, most depositional environments are like marine basins, right? That's where sediments go to be buried. I was going to say die, but sediment's already dead. So yeah, so marine canyons can deposit like fans. The continental shelf itself can deposit. We can have sediments deposited there. Alluvial deposits at the deltas of rivers, and then maybe on kind of these margins of the continents where it's pretty flat as well. And so, Garrett, what do you think? So, what do you see here? This is like a sand dune, right?
Mm-hmm.
And so we'll see, especially in Utah, that sometimes those environments can be preserved as well. To preserve the sediment and get a sedimentary rock, we have to bury it. That's the key thing. Otherwise, it's going to get eroded away and move somewhere else. Okay, so we're going to go through rock type by rock type. And the first one that we've got here is called breccia, B-R-E-C-C-I-A. Usually I would say, okay, let's ask the question, where do these form? And so take a minute and think about it as you're watching this. So if we were to describe these, they're very angular, right? The clasts, the pieces of stuff, which are called clasts within the breccia, are very angular. They can vary in size. They could be, we can see here, the smaller than a €1 penny, or they can be the size of a person, right? So what do you think, for those people online, if you want to pipe in, what do you think these are, where do you think these are formed, or where do you find these types of rocks? Okay, nobody wants to pipe in. All right, so Garrett, you want to try?
Yeah, I would say it's probably they look like the kind of rocks that are kind of that they're a combination.
They are a mixture of things.
You know, it's like you got a bunch of different rocks coming off of mountains and whatnot, and all collected in one area. And over time, it just kind of mold into one rock. But if you cut it open, you can kind of see all the different colors.
Okay, so Garrett said that, yeah, these must be in a low environment. He also mentioned that, I'm repeating because I'm not sure if the room mic's picking me up or it's just this one. Anyways, and it's probably associated with like the base of a mountain, and that's the key thing here. So the fact that they're angular shows us that the clasts, the sedimentary particles, haven't moved very far, because the further they go, the clasts would become more rounded before they're deposited. So wherever they're deposited it must be a low environment to be preserved, but it must be close to the source of where they broke off, because they're still angular. And so it tends to be that these are formed at the base of mountain cliffs and things like that. So the environments that we might expect to get a pile of those angular clasts could be off the base of cliffs, things like that. This could be a depositional environment, right? If this cliff was also a normal fault, which means this lower side is basically constantly moving down and burying itself. And so then it could get preserved if it's buried. A lot of times the environment, is the side of a hill where you see those types of clasts. It's probably not ever going to get preserved at that position, most likely. But we'll say never, not never, but most likely. So yeah, the clasts are broken off from the sides of the mountains, and they must be deposited fairly nearby to stay angular, to form that breccia. So some areas that would be potentially preserved would be like steep alluvial fans. So this is my brother standing on one of these type of fans in Death Valley National Park, and that's a valley which is fault bounded on both sides. So the middle of the valley is always dropping down, and so the sediments are constantly burying themselves. And so we preserve those sediments that just came from the adjacent mountains and are still very angular. And so there's another picture of such a fan really close to the rocks. And some of the deposits that form these are oftentimes less to do with rivers in the sense of water flow, right? And you can kind of sense that here. We see all these mounds of deposits, but where's the water? And then here's some other channels, but there's not a lot of water in those channels. So sometimes it's just debris flows, basically, which is there's water involved in the debris flow, but it's really kind of a mud, rock, and soil mixture going down the side of the hill. And they tend to happen after huge, kind of exceptional rain events, snow melt events, where the soil gets ripped out and all the rocks that are loose with it come down. Some other exceptional cases where we can get breccia, and this is kind of a rare thing in the sense you're not going to find tons and tons of this, but when you find a fault zone, if we zoom in on that fault, we can often see that within the zone of deformation, say if we move right into there, we see that underground as that fault was moving, kind of pulverized the rock into these angular fragments. That's called a fault zone breccia. It's not, by definition, it's a little bit weird. It's not really a depositional environment, but you can form breccia there. Some other places besides alluvial fans and fault zones would be on the side of like impact craters. So this is a meteor crater in Arizona. And on the sides of those craters, we can get these kind of flows of deposit from that impact. And that's going to be kind of one transport event. So the stuff is very angular. It's also not, it's a little different, right? Because the angular clasts are kind of spaced between like a fine matrix in this case, and not all just big clasts. And then volcanic deposits as well. These lahars can, and ash flows and things like that can look much like those other alluvial fan deposits and debris flow deposits. They're angular rocks, sometimes with a fine matrix inside of them. If those are preserved, they would form what we might call a block and ash deposit, or you could simply call it a breccia. Okay. So then this next type is also large class. So breccia was large class. Conglomerate is also large class. But what's the difference here between conglomerate and breccia? They're round, basically. So the conglomerate is a very rounded clast. It's clasts solidified together into that are rounded to form a rock. So the conglomerate's made up of many rounded clasts, and they can vary in size, again, from pebbles all the way up to boulders. They're cemented together, and all sedimentary rocks that are clastic are cemented in some way. In some cases, the cement is kind of a matrix of other fine rocks, but also there'll be some precipitate, some chemical precipitation. It could be like hard water, which is calcium carbonate, or sometimes the precipitate is a silicate, some silica deposition. But carbonate's more common. Yeah, so that's a conglomerate. Where do we get, what is a depositional landscape or environment where we find rounded rocks? What do you say? Where do you think? Rivers, right?
Rivers,
Yeah, cobbles and streams and rivers. That's, you know, a conglomerate. If somebody asked you what's the depositional environment for a conglomerate, great answer would be rivers, streams. Yeah, fluvial environment, river environment. Also, rounding can happen on beaches, right? So as the waves are smashing these rocks together, it's like a rock tumbler. We get them nice and smooth. So we need either a long transport process or a lot of work being done. And so the constant action of the waves can round the rocks as well. So a beach environment is also an acceptable answer. How could we tell the difference between a beach and a river in terms of the rock? That would be an interesting question. We might look for, in the beach, maybe we could find a seashell or two. Or in the river, maybe you'd find a more diverse array of rocks from many different parts of the drainage network, whereas the beach is probably going to be locally sourced rocks, maybe of all similar types. Some other kind of large classed rocks can be from produced from glacial depositional environments. So glaciers move all sizes of sediments. Basically, yeah, I mean, look at that rock on the right, lower right. That's what we call, sometimes those are referred to as diamictites or glacial tillite. But in the other sense, you could kind of either call it a breccia or a conglomerate, right? It's similar. It's got some angular stuff, some round stuff. It's somewhere in between. So we know the transport's been fairly far. The other thing about the glacial deposit is it's usually a mix of class sizes, so small and large, not very organized at all. And the stuff that's in the middle is usually dark in color. It's because it's made of soil, right? So that kind of organic, rich soil that's been moved along by the glacier. And then at some point deposited. Maybe the glacier went away. It like totally retreated from the environment. And the materials left behind, whether or not it becomes a rock, depends on whether or not it's buried in the end. But yeah, so glacial deposit can also form a coarse-grained sedimentary rock. So now we'll go to a little bit finer grains. So we're working from coarse to fine grains. So the next grain size below pebble is sand. And so here we have a sandstone. This is famous, the wave, right, on the Utah-Arizona border. These sandstones are a particular type. They're associated with dunes. So you may see this kind of repeating pattern, right, of these angular, we call it trough cross beds that you see here. Sorry, massive cross beds is what we call them. Trough cross beds are different. They're cross beds like this, but they form a trough. So these are massive angular cross beds. And then between each of those cross beds, you probably see this horizon here, which is relatively flat. And then we have another set of trough cross beds. Anyways, so what's going on here is all of these angular beds are basically as the sand was getting blown across the dune field, rising up over one dune and falling down the other side. If that dune was preserved, you're seeing as it's deposited on the other side. Of course, to be preserved, it had to be buried. And so there has to be some period of stabilization. Maybe the environment became wetter. And so imagine it did, and it kind of formed a soil over the top of it. And maybe part of the dune was eroded. And then we formed this soil, it held things in place. We formed this flat horizon. Oh, but then the environment changed again. It got drier, and we get more sand blowing over that soil. And we form another set. And so if that keeps repeating, then we can continue to deposit on top of, and they might get buried and preserved. And so in this case, it's a big sand dune environment for where these formed. So those are referred to as like ergs, E-R-G, same word for like rowing equipment. But it's having to do with big, massive sand seas. And so in Utah, in the Colorado Plateau in general, there was a huge sand sea here during the Mesozoic time period. It was a big, shallow ocean basin, and on the margins, it was quite arid. Other places we can, actually, I'll pause here for just a minute from the slideshow, show you one modern example of a big sand sea. So in Namibia, in southern Africa, down here at 25 to 30 degrees south, there's a huge coastal sand sea. You see that there? So this is the Namibian desert. Huge sand dunes in these areas with all sorts of patterns. And this is a whole nother subfield of geoscience to study how sand dunes form. And there's many, many, many types. But But some of these sand seas, and this one would be a good analog for maybe what it looked like in Utah if you went back 100 million years ago or so. Okay, so other places we get sands forming is obviously at beaches. So sandy beaches can be a host environment to form sandstone. But here we would expect to see different things. In the case of the sand dunes, it's very pure sand, just what's ever moved by this wind, right? In the sandy beach, we probably see some other things. So we might have the shells of organisms. We might have a couple pebbles here and there that didn't need to be moved by wind because they could be moved by water, which is a little bit easier to move bigger particles. So if we go back to sand dunes, show you a few more examples. So here we are again in Utah. Some of the beautiful Navajo and Wingate. This is the Navajo sandstone in southern Utah. I think this is a picture of that Namibian sand sea that's existing today that we looked at briefly in Google Earth. And then this is, I believe, Death Valley has some sand dunes. And this is White Sands National Park in New Mexico. And then up above here, this is the Great Sand Dunes National Park in Colorado. And so the Great Sand Dunes National Park is pretty amazing if you really want to see sand dunes and you've already seen the Little Sahara in Utah or coral pink sand dunes in southern Utah. This would be your next stop. So this is a 700-foot high sand dune. So it's pretty epic. Can also bring boards to go boarding down these. They even allowed dogs in this national park, which was amazing. I went there this past fall. Why is the sand dune here, right? It's not next to the ocean. It's not at like exactly 30 degrees north desert. So usually sand dunes need to have kind of an environment where it's pretty dry, because if you have wet conditions, then the soil is going to be kind of cohesive and hold things down. Here, this is in southern Colorado on the interior side of the Rockies, so to the west from Pueblo. And here there's a big, to the west of the dunes, there's a big volcanic complex, which is really easily weathered and eroded. And so those particles are really readily available to be moved across this pretty semi-arid area. We're kind of in this rain shadow of the western U.S., so it's pretty dry. And so all that sand has moved and flowed west, from the west to the east. So it's going by westerly winds. And then it hits the Rockies, right? Or I guess this is technically the Sangre de Cristo Mountains, but the winds die down. They can't make it up over the mountain. So of course it drops all the sand there. And so it all falls out there and forms that big sand pile. The white sands down in New Mexico is a different type of material, mineralogically. So most sand dunes are made of quartz or feldspar. That's pretty much all you're going to find in there. If it's different, so say at a black sand beach, something like that, then it's got to be close to its kind of sedimentary source, say a volcanic complex. In this case, this white sand dunes is a form of gypsum, which is the same stuff they make drywall out of. And it's really common as a vein in rocks. And it can be found in kind of salt flats. And so I believe the answer here is that it's coming out of some salt flats that were here in the past and then has been blown around. This stuff is really reactive with acid rain and things like that. It's a good question of whether or not we'd ever preserve a white sand in the geologic record. So if will we ever see a sandstone that is made of gypsum? Most sandstone rocks are made of quartz and feldspars. I've not personally ever seen any sandstone made of gypsum. And the reason for that probably is that it is a mineral that forms from precipitated water. So if you bury it and compress it underground, maybe where there's groundwater, it's more likely to kind of dissolve away, maybe never be preserved, potentially. So we might see it at the Earth's surface, but probably not in the geologic record. Okay, so other places where we might get other fine-grained sediments could be just simply in valleys. So we live in a beautiful interior basin like this. So I think this is out in Arizona or Nevada. But this basin and range environment where we don't drain to the ocean, right? We're in this great internally drained basin. All the sediment stays there too. The water doesn't go away, the sediment doesn't go away. So it fills up these valleys. If you bury the sediment a few hundred feet down or several thousand feet down, it's going to start turning to rock under that compression. And so we can form sedimentary rocks just within these internally drained areas. Doesn't have to be offshore in a marine delta or something like that. But that's another great place. So deltas, also the floodplains of rivers. But one common thing that hopefully is coming out from this, I keep saying, well, where are we going to preserve this? Where are we going to preserve this? As we look at a river, we see constantly that the river is eroding and depositing. So we get deposits of sandbars. Where did that sediment come from? Well, it probably eroded on the other side of the bank. And so that's why I keep saying this. So if we think about the geologic record and we're trying to interpret geologic history as we move forward in this class, 90-something% of what goes on the Earth's surface is never recorded in the rocks, right? It's eroded before that is preserved. And so we're only seeing a sample when we look at rocks themselves. But these basin sediments can be quite informative about depositional environments. Just the grain sizes of themselves, it's made of silt. Those sorts of things are deposited in kind of low energy environments, so the water's not moving very fast. Because if it's moving at all, the water kind of suspends silts and clays. But if it's really calm, then it'll settle down to the bottom. So calm water, we can learn from that. Also, sometimes within that, we'll see kind of wetting and drying things. So this is mud cracks. So mud cracks form right when the water all dries up and the sediment's mineralogy kind of contracts as the water leaves, and then it expands when it comes back. So the minerals kind of hydrate, and or the soils themselves do. Anyways, that can be preserved, right? If we have those cracks there and another deposit comes on top of them, then we can like peel off rock layers and find underneath, oh, the evidence of the ancient mud cracks. And so that tells us that the environment was kind of calm water. It went back and forth between dry and wet. So what might that be? Oh, maybe a shallow lake, like Great Salt Lake, kind of dries up sometimes, kind of gets wetter. Or another place could be like a lagoon where tidally, even diurnally, kind of tides come in, tides go out, gets dry, gets wet, back and forth. Some fine-grained clastic sedimentary deposits and then rocks are also formed in deeper water environments. And so that rock on the lower right is kind of this angular-looking rock in this format, but it's a shale. And the shales are usually formed offshore. So if we look at some other examples, if we look to the lower right here, that's kind of a tidal environment, right? And we can see the evidence of that. It's this really flat plain. You can see the vegetation is here. The water level keeps shifting up high and down low. We can have environments that are sort of similar, but they're not kind of controlled by tides, right? So in these interior basins of the U.S., we can get lakes where the lake level is shifting with the season. Bryce Canyon National Park, the sequence of rocks that you see here forming all these beautiful amphitheaters and things like that. If you look closely at the rock types, you'll see bands of color, but also the fact that the sediment size is kind of pretty similar throughout there. The color might respond to different chemistries of the past lakes that formed that deposition. And so all those are like big interior lake environments where that rock was formed. And so some other examples of these fine-grained sedimentary environments, mentioned a few of them, tidal flats and lagoons. So we can have, like, see the mud cracks there. And then here's, we have the beach out here, right? We can form sand there. But then back behind, we have these little environments that are kind of wet and muddy. And so the sediments there could be quite different than over here. And if you were to bury this all and form it into rock, then we'd see that spatially over some distance, the rock type could change quite a bit, right? You could just go a mile and see sand and see another place mud, mudstone versus sandstone. And so sometimes when we look at how geologists have mapped sedimentary rocks, they say, oh, this is the Navajo sandstone. When it says this is the Navajo sandstone, it's what we find, it's always sandstone. Other times you'll see that geologists call something the something formation, like the Chin-Lee formation. And what that's indicating to you is that the Chin-Lee, which is you'll find this rock in a lot of Utah's national parks, but especially like Capitol Reef. It's actually where a lot of the uranium mines were in Capitol Reef National Park. But it's not one type of rock. There's sandstone, there's mudstones, clay stones. And so it means that we had different depositional environments that are all representing that same time period, kind of alternating back and forth. And here's a nice river delta, another great depositional environment. Okay, so as we get further out into the sea, away from the fans, the energy of the environment gets much calmer. And so this is where we deposit really fine-grained particles. So we're talking about clays and muds primarily. Also, some of the deposition is not even, like, in a sense, not even classed. So we just have marine organisms growing in the water column, like plankton and algae, and dying in the water column. If it doesn't get eaten up by something, it settles eventually to the seafloor. And so some of the mass that forms these shale rocks that you can see up here, which you hopefully see are gray, brown, kind of black in color, is actually made of organic molecules as well. And so that's why shale is a great source rock for oil and gas. It's because of those organic particles. And so extreme end of this is what's called oil shale, where a significant percentage of the actual rock is still organic bonds and can even be set aflame. And so that oil shale is almost like an organic sedimentary rock, but there is still quite a bit of inorganic material in there, clays primarily, clays which are silicate minerals. If we go further to a different environment where we're depositing, in the case of shale, the organic matter is coming from plankton and algae in the water column offshore or in a big lake. In the case of coal, these are formed where you're depositing basically woody material. So woody material probably forming in swamps adjacent to maybe large river systems. So think about like the bayous down in Louisiana or Mississippi or something like that as an analog environment for where coal deposits come from. Because every year there, lots of growth happens, right? It's really biologically productive. New growth happens, old growth dies. The old growth dies and it falls into, falls into like these really still waters. They're what we call anoxic waters. There's not a lot of oxygen going around, which means that they don't break down biologically very much. And then also, it's adjacent to these big river systems. So sometimes the river system floods, and then boom, it puts a bunch of silt over the top of all that organic matter that was deposited and buries it. And then, okay, it goes back to being swamp. get more organic matter, another flood, and then we can preserve over time a sequence of silts and sands, organic matter, silts and sands, organic matter. And then we get this sedimentary sequence which has beds of coal within it. So coal is that compressed old woody material. And so that is literally an organic sedimentary rock. Remember, it's not a mineral because it's organic, but it is a rock. Okay, so yeah, go ahead and ask a question. Sorry.
So pretty much everywhere that we found coal used to be a swamp at some point.
That's the likely answer, yeah. Most places where we find coal was at one time a swampy environment. It was most likely a very kind of flat environment, so not mountainous. That's pretty sure. And probably adjacent to a big river system. It's also probably it was slightly more biologically productive than a place like Utah. So it was probably more humid climate is the other thing. So we have to get a lot of material dying every year and growing. Yeah, great question, Jacob. Any other questions? Okay. So not all sedimentary rocks are what we would call clastic, which is what we've been looking at before. So the clasts could have been organic or inorganic. But now we'll think about another type of sedimentary rock, which is referred to as chemical. So chemical sedimentary rocks are made from chemical precipitates. So what that means is minerals formed from a water solution. So when we think about like our salt lake, that's a great environment to form chemical sedimentary rocks. And if you go out to the salt flats and you pick up a hunk of salt, that is literally a chemical sedimentary rock, the salt that you're looking at. There's many different, of course, types of salts, and so we could describe them in detail, but you don't have to do that for this class. Where does that salt come from? Well, it's really just coming from dissolving rocks somewhere along the way, rocks and soils, right? So when we think about the weathering of rocks, a lot of it has to do with water interacting with the rock, taking some material from that and transporting it away in the water. When it gets to environment where the water dries up, salt is going to be deposited, or whatever chemicals are in there. And so that's how we get our chemical sedimentary rock for the most part. You can also get replacement of material underground in burial. So in the case of petrified wood, which is, we have a lot of that in Utah, in Arizona, etc. That is also technically a chemical sedimentary rock. Petrified wood is usually replaced. So there's no organic molecules when you look at a piece of petrified wood. It's all some other mineral. And so that chemical deposition replacement is that chemical sedimentary rock deposition. In this case, usually petrified wood is made of silica deposition. It's really hard. Some other places to get them. So in springs, in lakes. So this is, I believe, Mono Lake in California, which is kind of near this big volcanic area, has a lot of underground heat. And also there's a bunch of faults nearby. There's a lot of water moving around. We have high mountains, the Sierra Nevada to that side. And within this depositional basin, there's lots of places that water bubbles back to the surface. When it does so, it goes from under high temperature and pressure underground, coming to the surface, colder, lower pressure. It tends to precipitate out chemicals that it's dissolved along the way. And so we get these tufa formations. Sometimes it's made of like calcium carbonate, and that forms what we call a travertine formation. Some people might have travertine countertops. It's similar to marble, but it's different. Has a lot more holes and things. Those are from deposits and springs. And so also there's a cool place to go look at. You can go hot springing up in Midway. I'm trying to remember the name of that place. There's Homestead Crater, I think it's called. That Homestead Crater is entirely a big spring deposit. It's a chemical sedimentary rock. And then on the other side of things, so we can have organisms producing chemicals to make sedimentary rocks. And so the classic example is limestone, which is made of calcium carbonate from seashells. So the seashells can be macroscopic, like you see here, and then stuck together, essentially. So they're basically clasts of shells welded together by deposition. That is limestone, but that's not all limestone looks like. So limestone can be associated with kind of really productive reefs where almost everything there is some sort of organism with a shell. And so these tend to be offshore. Oh, but I don't have a great picture here, so let me show you a couple other limestones. So some limestones look really boring, and actually most look like this. Okay, so let's open image. There we go. So yeah, a lot of limestones just look really drab and gray. These are referred to as micritic limestones. So they're form of calcium carbonate. The origin of that calcium carbonate is from sea organisms, but either the organisms were near microscopic and the shells fell to the seafloor, or in some cases, sometimes the material kind of dissolves in the water column, and then as like the water turns over, it kind of reprecipitates near the bottom of the ocean as like this slimy ooze. It's also usually mixed with mud and clays, and so it's not pure calcium carbonate, but it looks like that. Sometimes you'll find a big shell mixed in, and that's what you'll see a lot if you go into the mountains here of the Wasatch. You see these limestones that look drab and gray, but every now and then you find a cool thing in there, like a piece of coral or a big shell or some other things like that. Yeah, I am usually pairing this with an activity for you all, so we're probably going to end pretty soon today. I'll mention one other type of biochemical sedimentary rock. You guys have heard of diatomaceous earth, perhaps? Diatoms are little organisms that instead of having a carbonate shell, have a silica shell. So let me just show you what diatoms look like. So maybe you've seen images like this. Image new tab, there we go. Yeah, so these are microscopic organisms. They have these really cool, radically shaped things. You can't really see them like that unless you look under a microscope, but it's made of silica, so similar to quartz. And when those things die in mass over time, they can form enough of that to form a sedimentary deposit too. And the sands that you find in some lakes, like perhaps even some parts of the Great Salt Lake, are pretty much just diatoms. Not really much in the way of sand coming from the mountains. It's more diatom shells. And so if you formed that into a deposit, it would primarily be made of biochemical sediments. So that's kind of cool to think about. Yeah, so to kind of wrap up, in terms of sedimentary rocks, we have three classifications. We have clastic, which is formed of different pieces of rock broken down. We have chemical, which is formed from mineral precipitates out of a water solution. And we have biochemical, which is formed from organisms and then fit together. And the whole point is, can we look at the details of the rock and figure out what was there in the geologic past? Okay, so I'll stop there, and next class we'll have an activity in class, so please be here for Monday, where we'll interpret some of the depositional environments for rocks that you find here in Utah. So what was it like in the past here, based upon what you see for fossils and other things? Do you guys have any questions online? No questions online. Okay. Well, in that case, you guys are all free to go. I'll stop the recording and end the meeting. If Garrett has questions, he can ask me personally. Okay. All right. See you all on Monday. And try to work on your journals. Make sure I did grade another journal, so get your Sedimentary Rock journal to finish up now. Hopefully this helps with that. All right. I'm going to stop recording.